Hello everyone. My name is Virat Gautam, and today I'll be explaining one of the most important concepts in linear algebra, and that is eigenvalues and eigenvectors, along with their connection to Python and real-world machine learning applications. Eigenvalues and eigenvectors form the mathematical foundation behind many algorithms used in data science, dimensionality reduction, facial recognition, and much more. So this presentation bridges the gap between the abstract mathematical ideas of linear algebra and the practical computation we perform in a coding environment like Python. We'll explore what eigenvalues and eigenvectors actually represent, why they are important, and how they give us insight about matrix transformation. So let's first we'll look at the fundamental concepts, understanding what eigenvalues and eigenvectors truly are. Secondly, we'll explore about geometric intuition and see how matrices transform in space and why some directions remain unchanged. Then we'll move on into manual calculations using a simple 2 cross 2 matrix. This will help you understand the computational process from scratch. Next, we'll see how these calculations are done in Python using NumPy. And finally, we'll look at real world implication, that is how PCA uses eigenvectors to find the principal databases in a database. So why eigen decomposition is important? Eigen decomposition is one of the most powerful tools in mathematics and data science. In principal component analysis, eigenvectors represent the principal directions of variance in a data set, and eigenvalues tells us how much variance each direction contributes. So even Google's PageRank algorithm relies on eigenvectors. The dominant eigenvectors of the web links metrics determine how important each web page is. In face recognition, we use something called eigenfaces, which are eigenvectors of the covariance matrix of face images. So understanding eigenvalues and eigenvectors give us insight across multiple fields. So now understanding the core eigenvalue equation. So below is a very powerful equation. Here, here A is a matrix that represents some linear transformation. V is a vector that maintains its direction when transformed by A, and lambda is the eigenvalue, the scaling factor. This equation tells us that applying A to some special vectors results only in stretching or shrinking, not rotation. So every matrix transformation, some kinds of stretches or performs rotation or change in the space, but when it's about eigenvalues, it does not rotate. It is just the scaling factor. So thus this equation tells us that applying A to some special vectors results only in stretching or shrinking, not rotation. These special vectors are the eigenvectors, and the amount of stretching is the eigenvalue. So now geometric intuition, that is invariant direction. So to understand this visually, imagine a matrix along a 2D plane. Most vectors will be rotated or moved around in different directions. However, some vectors, the eigenvectors, keep the direction same even after the transformation. They may get longer or shorter, but they do not rotate. These fixed directions are very important because they reveal the structure of the transformation, and the eigenvalues tells us that exactly how the vector is stretched or shrunk along that direction. So now let's understand with an example. So to make us understand, let's take a simple 2 by 2 matrix, which is this matrix. We'll find its eigenvalues and eigenvectors manually. This will show us exactly how the process works step by step. Our goal is to find all vectors such that a matrix multiplied to vector v results in a scalar times the vector itself. So these are the invariant directions under this transformation. So let's formulate the equation. So we start with the equation, uh, this equation, and we'll bring all them to one side. And we know if we if we multiply any vector with the identity vector, we'll get uh, the same vector, right? So we can multiply with the identity vector on the once we bring on the left side. So this equation can have non-zero solutions for v only if the matrix, this part, is singular, that which means that its determinant must be zero to for this equation to be satisfied. So now form the characteristics equation by we'll just plug in the value of the vector A and setting the determinant of this will calculate its value, and we need to now calculate the determinant. Setting the determinant of this matrix to 0 give us the characteristics equation. This is the equation whose solutions are the eigenvalues. So now let's calculate the determinant. So so to calculate the determinant, now we compute the determinant of A minus lambda times the identity matrix, which is which will expanding us on expanding will get this value, and which is a polynomial value. So we'll get this characteristics polynomial value. This quadratic equation is called the characteristics polynomial. So solving it will give us the eigenvalues. So now we can solve this polynomial equation using the method below. So if we solve this, we can factorize this into this equation, and if we solve solve this equation, we'll get the first eigenvalue as 3 and second eigenvalue as 1. So this value tells us that the scaling factor along the direction of matrix A is 3 and 1. So now let's calculate eigenvectors for when the eigenvalue is 1. So to find the eigenvector for we need to solve this equation. So we'll just plug in the value for the eigenvalues, and we already have the value of the matrix A. And now so this we can see if we solve this equation, we'll get this relationship. So x will be equal to minus y. So if we plug it, we'll get the value that if we plug the value, we'll get the vector minus 1 comma 1. So this would be the first eigenvector associated with the this eigenvalue. So now similarly for eigenvalue of 3, we'll get this will yield the equation, this equation, and we'll have y equals to x. So if we plug in any values for y, we'll get the x. So second vector would be 1 comma 1. So these two are the vectors, eigenvectors. So now so this was about eigenvectors and eigenvalue. Now we'll implement it in the code. So in the next part of the presentation, I will switch to Jupyter Notebook, where I'll show the Python implementation using Python implementation of real world implementation of eigenvectors using for PCA principal component analysis. So let's move to the Jupyter Notebook. So first, let's understand what is PCA. So now that we have understood eigenvalues and eigenvectors, we are ready to see how these ideas are used in practice. In this final part, we'll implement a principal component analysis or PCA using the breast cancer dataset from the scikit-learn. So let's understand what PCA actually does. So PCA is a dimensionality reduction technique. Instead of removing features, PCA creates new features called principal component, which are linear combination of the original ones. These components capture the maximum variance in the dataset, while eigenvalues and eigenvectors are of the covariance matrix. So let's first step, let's import all these library, and let's begin by importing all these library. We'll need NumPy, Pandas, Matplotlib, and Seaborn, and the PCA and the standard scaler as well. So first let's import those data. So we have here imported the PCA. So now so then we'll load the breast cancer dataset. We'll load the data using the load data breast cancer dataset function. This dataset contains about 30 features describing the numerical. So we can see these are the features for the dataset, which describes the numerical nuclei measurements along with the target indicating whether a tumor is malignant or benign. So once this data set is loaded, so we need to let's con- uh, let's this is the information about the data set. So now let's convert into the data frame. So if we convert into the data set, we this is the data set. So now, so we need to scale this data set. So why we need scaling is PCA is sensitive to features scale. So features having large ranges dominate the variance. So before applying PCA, we need to standardize the data set uh, so that every feature has mean of 0 and standard deviation of 1. So to for the standardization, we import the standard scaler and we then fit data frame. And once this is scale scale, we need to transform the data as well. So if we look at the scale data, this is how it looks. So now we'll apply the PCA and reduce the data from 30 features to two principal component. These two components will capture the maximum possible variance in just two dimensions. So let's uh, initialize the PCA. So and then let's fit the data. And if we after the transformation, we get the new data set will with only two columns, the PCA1 and PCA2. So if we print the PCA, we'll get these values. So these are the only columns, two columns in which our whole data is represented. So if we print the explained variance, so PCA also tells us how much information each principal component preserves. So if we print it, we can see that. So for example, PCA1 may capture around 41 or 13% of the data and of variance, and PC2 about 15%, 5%, 5%. And these two components preserve over 25% or yeah, so 20% of the data set. So there are other, if we could have created other principal components as well, but for this tutorial we are using only two. So and only two, we have reduced from 30 dimension to the only two dimension. So if we want to visualize the PCA result, we can finally visualize the data set in just two dimension. So if we plot those data set and principal components, we'll get these visualization. So each point represents a tumor case. plotting uh, Plotting using PC1 and PC principal component 1 and principal component 2. The color indicates whether the tumor is maligating or banging. So in this plot, you can clearly see the separation between the malignant and banging cases, right? So if this is the kind of data set, we can easily apply multiple any of the classification algorithms such as um, the SPMs or logistic regression as well. So this is possible because PCA rotates the feature space using eigen vectors in such a way that the maximum variance become visible in fewer dimensions, as we can see here. So now earlier so let's connect back to the eigenvalues and eigenvectors. So earlier we learned that eigenvectors give direction and eigenvalues tells us that how important those directions are. So PCA uses exactly these. Eigenvectors are the principal component direction and eigenvalues are the explained variance of each component. So PCA is a direct application of eigen concepts we have learned. So in summary, we scale the data set, extracted two principal components using PCA, visualize them, and saw how much variance they capture. This shows how eigenvalues and eigenvectors power. This shows how eigenvalues and eigenvectors power real machine learning tasks like dimensionality reduction and feature extraction. Thank you.